Good morning, and colleagues, friends, and students. My name is Yiguan Ju. I'm from Mechanical and Aerospace Engineering. Today, I have great honor to introduce our National Lab, a lecture series speaker of Dr. Ahmed Diallo from Princeton Plasma Physics Laboratory. Let me introduce briefly about a research experience of Dr. Ahmed Diallo. Ahmed is a principal research scientist at the PPPL, and he leads at the topical science group of pedestal structure and control of National Spherical Torus Experiment at the NSTX, and also conduct advanced laser diagnostic divisions and lead that division as well. He's the Deputy Director of Innovative Network of Fusion Energy, which is a DOE and Fusion Energy Science private-public partnership program. Previously, he performed his a postdoc research at Swiss Federal Technical Institute and was a research fellow at Austrian University. Dr. Diallo received that Department of Energy early career grant, which is very difficult and a very competitive, great honor for him. And to control that a pedestal for maximum fusion performance. His research interests range from low temperature plasmas, ion thrusters for space propulsion, and to fusion energy sciences. More specifically, Dr. Diallo's research focused on the age of multiple tokamaks with the goal of understanding of L mode to H mode transitions. The formation of H mode pedestal and the inter-ELM instability, as well as the control of the onset of the ELMs. That is very important for future fusion reactors. Today, we are so pleased and to have a Dr. Ahmed Diallo to tell us about the fusion energy conversion. Ahmed, I transfer the microphone to you. Welcome, thank you.
Thank you very much for this introduction. So I thank Julia for inviting me here. This is really, I wanted to see it more as an informal conversation with MAE about what we do at Princeton Plasma Physics Lab. So I'll brush up on the fusion science a little bit and go down to the microelectronic. So just because for a student, I wanted to give a little bit of background, where I'm from, where I came, a personal background specifically. So I was born in Moscow, Russia, lived in Burundi. To give you a sense, if you look at the middle panel here, this is a country on the east side of Africa. And I'm originally from Burkina Faso, lived in Nigeria, Saudi Arabia, and Nigeria. And then finally moved to college in the US back in the 90s. End of 90s. Let me remove this. If I can remove this first. Okay. So that's to give you, that's really the essence of where I come from and all the different experience I've had as I grew up, and then finally decided to move to the US for college because I was interested in physics. Now, what inspired me in the scientific journey really was probing the key fundamental element that is really at the heart of nature's self-organization. So that started really early when I was at the University of Ouagadougou, which is Burkina Faso, where I obtained a DUG, which is like a degree you get in math and physics before you move to engineering school. And then finally, I decided to switch career after that to go to physics at University of Montana, where basically I discovered plasma science through what's called, what you may or may not know, some of you may know, is the NUF, which is the grandfather of the SULI program. Basically, it's a research experience for undergrad. So I got immersed in plasma science. I went to Princeton University to PPPL for plasma science, and really discovered and really got really excited about the fusion concept and the collaborative aspect of it. I thought that was great mind getting together, chipping away at the problem. So that led me to moving to Iowa for a PhD in physics, where effectively I contributed I just effectively built this system here that you see at the bottom panel here, the left panel, which is like a linear magnetized plasma. And that was back in 2000. I started my PhD journey building the system to be able to get a uniform plasma to basically, and the goal of my thesis back then was effectively to look at the ion phase space and look at the smallest possible measurable plasma fluctuation in order to get the degrees of freedom of plasma. And then from there on, build on, once you have the degree of freedom, or what are the possible instability of where the energy flows. So that kind of allowed me to kind of dabble a little bit with laser-aided plasma diagnostic, for which I really got excited and then started taking on. So this system still exists. It still produces grads through the University of Iowa. And actually, last time I visited, it's kind of nice when you build a system, you look back and you realize all the mistake you made. I could have done this a little better, but it's all you wanted back then is your PhD. So the system is there and as is, and a few modifications have been made, but really a very nice system. So then once I had a linear device, I was a little bit challenged by post-PhD. I went to university, to the Swiss Federal Technical Institute in Lausanne, where basically you take this linear device and you wrap it around as a simple magnetized torus. It didn't, so basically you wrap around and you're gonna start having gradient field. But you know, it was to me complex enough, not as complex as a tokamak, but just to keep my feet wet before we get into a tokamak environment where there's less and less freedom to change stuff. And basically you are assigned a port and you work with it. So there I was very interested in wave excitation. As I said in PhD, I looked at the degrees of freedom. And now the next big step for me was to look at how do I pump energy into these different degrees of freedom to excite this mode. So, and then ultimately, one of the aspects was also to apply laser-induced fluorescence to be able to track the modification of the ion distribution, and therefore, as you change the distribution, you're going to have from the different moment of distribution, different mode that will pop out, and also you can look at a heat transfer. So that was things that I got interested. So I spent 2 years there, produced some papers there. It was a very interesting project, and it basically for me, it was the next step in complexity, geometric complexity, and also adding physical complexity, that is gradient of field. Then I was sitting once in my office, Switzerland, and I basically was reading about polarization spectroscopy. And that's something that caught an eye on me, and I started reading up about it. And turns out there was a position at the Australian National University to develop this very same system that is actually right now has taken off, which is like coherent imaging, basically using interferogram, basically looking at the light polarization and basically inferring flow velocity. And also actually what we did as a first initial test in Germany, I was in Australia, but I went to Germany to test that on a tokamak called Textor. We were to look at a pitch angle measurement. So it's an imaging diagnostic that kind of relies on birefringent crystals. And so that got me really going into getting to understand what can we extract from polarization spectroscopy. It's more of a remote sensing approach applied to fusion devices. So that was where I started dabbling in fusion of science, and got excited about it and moved to the NSTX at PPPL, where basically I was doing tons of scattering and got interested in edge physics. And I'm showing the right panel here, a cross-section of a D3D, which is one of tokamak in the West Coast, General Atomics, and then basically also a cartoon or the region that I'm mostly interested in, which is really right at the edge where you have most likely gradient, and that's where you have heat transport across that boundary. So that's post-PhD. Now, once the PPPL, as you all know, the mission is very clear. So it's solving crucial scientific and engineering technical challenges and for fusion energy. And it's a collaborative institution. It's a national center that has two couple missions here. The first one is understanding the plasma from nano to astrophysical scales. And that's the second one is to enable fusion to power the US and the world. So this is a design of the Princeton Plasma Innovation Center, and it's hopefully going to be built soon, but we're going through the design review at the moment. And this is really exciting moment because as we go, we try to improve into, we try to expand into all the microelectronic or nano. So let me throttle back here in fusion. For the student that may or may not know, the fusion require very high temperature. This is a slide from Menard, who is the deputy director at PPPL at the moment. So you have three graphs, and the DT is deuterium tritium, and DD deuterium cross-section line here, and D helium-3 here. And you can see that effectively on the y-axis here is effectively the fusion difficulty, which is pressure time confinement. And then the x-axis is the temperature here in million Kelvin. So you really want to minimize the difficulty, obviously, and not require high temperature in this case. So, and one of the metric that has been used is the triple product, which is really tau E, which is confinement electron temperature, which needs to be about 8 atmospheres a second. So that gives you a sense of the difficulty of fusion. And one of the main concepts that are out there are what's called a tokamak, which is really coming from the Russian, and then the spherical, the stellarator, which kind of was born here basically at Princeton. So they all have their disadvantages and advantages. Tokamak advantage is really best confinement. This is the well-studied configuration. The coils are simple to build, and then the stellarator has an advantage that is no current driven. So there's nothing necessary for driving a current, and is more stable. However, they all have disadvantages like any kind of system. For the tokamak, you really have to drive a current, and then some megaamp type current, and prone to disruption or rapid loss of plasmas. And really, that needs to be addressed before we move to a power plant. The stellarator has not been studied as long as the tokamak, and you need to build complex core, and then you have to think about exhausting the heat that you get. But there is currently permanent magnet stellarator that's being designed, or at least thought through by Steve and al. And that's something that we hope that can kind of facilitate or make this complex configuration even reduce the complex configuration this way. So I'm going to move to ITER because that's a tokamak. That's one. And ITER is really what we are, as NSTX, we're trying to aim the research toward as much as possible as a focus. And recently, the assembly of the ITER tokamak started officially. So that was a big, exciting news. And really the goal of ITER at the moment is to really to access, first of all, burning plasma and study it so we can go to a reactor. And so ITER would like to produce the goal is to Q equal 10, which is fusion to external heating to be a factor of 10. And so that is work that is being done. And we're all looking forward to this machine because it's going to really advance our physics understanding. And that's going to allow us to kind of extrapolate to the next reactor to put electricity on the grid. But going forward, there are two essential things that one needs to worry about. Okay, it's good to study the burning plasma, that's essential, and ITER is the best approach. But really, there's still small devices at the moment that we need to make, that we can study in order to make, to move toward an economical electricity production. So the goal is really to study how the physics and engineering prediction, most likely. And that's something that's always been an interest of me, is like taking a simple system, break down the complexes in a simple system, and try to see if we can understand the physics, and therefore we can move on to extrapolating for fusion reactors. So to give you a sense of what we're doing here, like I said, we target high fusion power, and fusion power density is proportional to plasma pressure square. And you have this beta, that is a term that we use, is plasma pressure to magnetic pressure. So as you increase beta, which is basically you start getting limited by MHD stability like ELM, like Professor Hugo said earlier, edge localized mode. There's also, you can increase the magnetic field. This is a configuration that a private company in fusion called Commonwealth is trying to do. But right now, what we are trying to do, we try to limit B field to a few Tesla, to 1 or 2 Tesla. and try to maximize beta here. And then by doing this, you can increase the fusion power. And so that's the term we are focusing on. And there are two avenues for this. You can kind of vary the aspect ratio, or aspect ratio is one of the three parameters. Just really the scale of the machine, if you think about it. And you can see here is the major radius to the minor radius. So you can see that the middle piece is a small aspect ratio, which is mostly, like I'm going to discuss next, is NSTX. And then the larger piece is more a conventional tokamak, which is more like ITER or most of the tokamak that are out there at the moment. So, so now what we focus on is ST, the spherical tokamak, because we can increase elongation. And by doing this, you really can improve stability and confinement. And that is a route that Princeton chose to go to with. And so, and NSTX really is the machine. So another advantage is for a spherical tokamak that is hosted at PPPL is effectively that you have the magnetic field line that spend most of its time around the center column, which is very stable, as opposed to a tokamak where most of the field is unstable, but outside the last, meaning on the outside effectively. So I won't bore you too much with these details here, but to just give you a sense, a flavor, there are two approaches, ST and a tokamak. They're all in the tokamak family if you want to, but they're slightly different configuration. And one allows you to achieve higher beta toroidal, in this case, 10 to 40. And so we try to take advantage, and it's a little compact. We're trying to take advantage of that for the fusion, for production of fusion down the road. So those that haven't been to PPPL, this is an aerial view of NSTX that is currently in construction for an upgrade. So it's a really nice system for understanding the spherical tokamak. So what you're seeing here is location of the first neutral beam, and also all the RF system that are piped, that the plumbing that you see here, that basically are used for heating plasma also. So the biggest upgrade that we're doing to NSTX, to give you a sense, is really increasing the size of the solenoid, the central magnet, if you wish, but also adding a second neutral beam which provide heating to the plasma. So with that, we plan, the reason behind, the motivation behind it was to increase the temperature by heating more, but also by doing so, that allows you to really get to a regime that's called that is a low collisionality regime, and that's going to be extrapolable to a fusion reactor. And also, one of the things we want to do by adding the second beam is to go to full non-inductive current drive. That has not been yet demonstrated on a spherical tokamak. So that's an advantage we like to add. And that was really motivated also, or that also came about by all this the scaling analysis that has been done, which here is collisionality on the y-axis and the beta t to tau e, which is a confinement effectively. And you really want to be a high confinement as possible, but very minimal collisionality. And that's really favorable. And NSTX showed that effectively we have a scaling that is slightly different from the conventional tokamak. So the question that we want to address is, okay, by upgrading this machine, are we gonna go even lower collisionality? If so, that's good. Then we extrapolate our scaling to a fusion reactor, as you see here on the left-hand side. So overall, this is really exciting time. If once we get the machine online, this is one thing we're gonna test fairly rapidly to see where we are on this curve. So, but to get to low collisionality, there's a lot that are needed. You need a higher plasma current, toroidal field, heating power, but also density control. And that's what I would like to start my hook with. Why I'm interested in this is the research that could be done in an STX for some other student. So density is really control is required, and to do that, you really need to understand the fueling. So you can see here on the right-hand panel, which is a plot of a researcher, Saskia Mordek, 2020 here. Basically on the D3D tokamak here, that was done, an experiment that was done on D3D tokamak, but also on the MIT tokamak that got shut down. basically you change the fueling and you can see different electron density profile as you go. So this very clearly, they seem to have an effect as you change the fueling. Fueling, I mean like puffing gas, putting gas in the edge of the plasma. So we know the plasma edge, like I was telling earlier in the discussion, the plasma edge really is an important parameter in determining the fusion confinement. So we really need to control that to a certain granularity. So heating the plasma will increase the temperature, but the fueling comes from the edge, and we need to understand how it fuels and forms this edge. And this edge, by this edge, I mean this little narrow pedestal from 0.2 or to about 1. So because that's what really drives, the height of that drives the plasma performance. So there is work that have been done. Understanding the neutral is something that has been tricky. We usually put deuterium gas. So there is work being done at D3D, actually, and I think there's a big push for that. It's using Lyman alpha, so the Bellman series effectively. It's a passive spectroscopy. Is led by the PPPL and D3D and MIT team at D3D. And there's really good success by looking at the neutral. But what we are trying to do with some of the MAE colleagues here, Schneider and Arthur Dogario here, it's to look at laser-based neutral measurement. And so we are looking with Fang, a student at MAE, the Rayleigh scattering approach, and we have a paper in line. Actually, this is something that we've been working for about a year, a little bit more than a year now, to try to do that. And then we started a new project with femtosecond TALIF approach with Arthur to see if we can fairly directly probe the local neutral density to be able to kind of provide, to validate some of the modeling that is available out there for predictive modeling, and to come up with a predictive modeling down the road and expand that for fusion reactor. So, but these approaches are not only limited to the two configurations that I gave you. As I was introduced, there's also private fusion devices that are out there. They too need to understand how fueling affect their confinement and so forth. So this is not only limited to the National Lab, but it is actually the seed. If we can show that these measurements are valid, we can effectively extend that to fusion devices, the private fusion devices, and also give them a chance, in a sense, to advance fusion energy. So there's based on where I'm coming from, I mean, in our division, for example, we are looking at also other needs that I think are crucial is internal plasma current measurement. I mean, there are other approaches called emotional stark effect, but we're trying to find, can we think outside the box to be able to probe the plasma and access the current that are in the plasma, because that really, as I told you earlier, has a big impact in understanding how the currents redistribute and so forth with true measurement, as a big impact for predictive capability on fusion reactor. So that's the fusion aspect. I know next week you're going to be having Nate Ferraro also, that's going to talk about other aspect of PPPL, but I wanted to focus more on experimental mode of plasma science and technology that I think has a lot of overlap with the MAE department. Now, the next thing that I would like to switch gear here is more on the microelectronic. So as you know, we are trying, we're expanding actually PPPL to look more on a microelectronic low temperature plasma, and we try to be responsive to the national need in this case. So as you can see, this new PPPL Innovation Center will be really very interesting, because it would have labs for microelectronic R&D and low temperature plasma application to try to be competitive out there. And also we'll continue our basic energy science. And obviously we already have a lot of advanced lab for reactor for fusion, NSTX, or for example, ITER. We did procure stuff from ITER. So that gives you a sense where we are going and why there's excitement for microelectronic low temperature plasma in particular. So I'm going to switch gear here, and one aspect of microelectronic is to throttle down is EUV lithography that we started about a year ago now, which is really something challenging. To give you a sense, and I apologize for this this picture. I thought it was better, but I guess my screen is better. The quality is not that great. The y-axis is the temperature, and x-axis is the plasma density. The EUV is right at the top at 10 to the 17. It's right below the solar core effectively. So fairly low, high density, but fairly low temperature in this case. So there is a big push to understanding of the UV lithography because there is a plasma, the laser plasma interaction in this. And we're trying to improve the understanding of the coupling and therefore the increase of the EUV photon, that is 13.5. That is kind of really the holy grail for making plasma chips. So there is a lot of physics that I explore, a lot of fundamental questions that I explore in physics, both in chemistry. And we, as at PPPL, have, I mean, just to give you, first before I switch, I give you how it works effectively for those that are not aware. It's basically a CO2 laser that is driven onto a tin droplet. And then from there, you collect that with a Bragg mirror and you focus down onto a chip effectively. And by the dosage that you have, you can really, they basically use that to build chips with masks and so forth. So we are not at PPL trying to replicate this, but what we want to do is understand the fundamental science to be able to extrapolate and increase what's called the coupling efficiency. And here the coupling efficiency is the number of photon you get from 13.5 relative to the number of photon CO2. At the moment, the best best company does about 7%, which is pathetic at the moment. So how there must be a fundamental limit. From the theoretical background, fundamental limit is about at 20%, but experimentally we are not there yet. So what's the physics limiting that limits this to us to achieve at least 20%? So we started investigating this, and basically this is really something we're pushing through at the moment. We would like to provide physics support to optimize this performance, the coupling efficiency. So we'll focus on identifying and validating key mechanisms responsible for target conditioning. And what I mean by target conditioning here is you really have a 50 micron tin, molten tin that comes in, and then there's what's called a pre-pulse that basically spreads the target before you hit it with a much larger pulse that is CO2 laser. So can we change, and then when you look at the physics effectively, you look at that it's only a small coronal aspect of the tin droplet that is ablated, and the rest is unchanged. So there must be a way to optimize that to increase the number at 13.5. So we'll also do initial calculation using PIC code. So we'll do a laser shape effect. That's something we're planning to do. And we'll try to leverage the setup at a PPL to validate models and develop reduced model that could be used at large facilities such as ASML, which is the leading Dutch company at this moment for EUV lithography. The competitor is Gigaphoton, and also we have what we like to do is we'll discuss with them if we can use a facility at the moment. If we're still in discussion, provide diagnostic development expertise such as picosecond Thomson scattering or advanced X-ray diagnostic. And obviously train student. They're hungry for a student, so there's some training capability that we can be provided at PPPL. So the reason we have in bits and pieces, we have a range of expertise, liquid metal expertise, lithium, this is a big strength of PPPL, X-ray also. Laser produced plasma is something we're starting, but we're building a core expertise, and laser aided plasma diagnostic, obviously. And then of course the modeling capability, as you know, through PIC code and radiation model that we're gonna pick up from other facilities. So we started with an experiment. The laser setup is really a lab that we inherited from CARS, which is like coherent Raman scattering. So we can at least start there, and then as we get some result, we'll probably build our own lab. But we have all the elements to really begin pulse shaping, capable, advanced diagnostic and simulation also. And now we're gonna effectively work with tin at the moment and ultimately try to see if we can have lithium at some point, since we have the capability for lithium. This is a planned capability. So from the modeling part, that's also something of interest. Since we want to identify and validate key mechanisms responsible for the target conditioning and laser tin interaction, we started thinking, and this is in collaboration with Will Fox, as PPL scientist, looking at plasma simulation code. This is a code developed in New Hampshire, but that was heavily validated against high energy density plasmas. So that will be modifying this code effectively to apply that to lithium, to laser tin, which is really close to a high energy density type plasma, except the laser is not as powerful. This code was used to look at self-generated magnetic field and dynamos and formation of collisionless shock and kind of streaming ions, and also to look at plasma transport according magnetic field. So basically, a code that is used for high energy density plasma, and basically we're trying to modify this code to adapt it to a laser tin, and then we'll have in-house capability at PPPL to do effectively modeling and validate with experiment, either on-site at ASML with a much larger device, or a prototype device that we're building at PPPL. So I might skip this. This is just a benchmark exercise we've done that Will Fox and his team has done. Basically, that's to show that using the PIC code and comparing that with the Draco, which is a different code, you have very good agreement here on the blue and the red curve here on the middle panel. So that builds the confidence that this code could replace Draco, which is like radiation hydrodynamic simulation, much larger code, but that doesn't have a lot more element, but difficult to run. And then hopefully with a small, compact, and reduced model, we get the same result, and basically we can use that to inform our next experiment we want to do. This is also the same thing, similar. The plasma simulation code was used, and it was found that it can retain multi-ion multi-stream effect for collision-less shock formation. In the middle panel, what you see is a Thomson scatter measurement, wavelength on the y-axis, and then x-axis the time. You can see this hook formation effectively that was reproduced using the plasma simulation code on the right-hand side. So that gives, again, more confidence that this code is kind of mature, ready to go. So it's very decent agreement, at least for scaling purposes. One can use this code to back out our experiment. So this is a possible topic that could be studied, the kinetic effect on a higher energy ion distribution during ablation for debris mitigation studies in EUV. I did not really say, but there's a lot of debris. Like I said, there's only a thin layer of the tin of 50 micron that is ablated, the coronal aspect of it. The rest comes as debris and as high energy ions. And usually the state of the art at the moment is to kind of put a buffer gas to absorb all this debris. But putting buffer gas obviously start attenuating your 13.5. So there's a trade-off to be made there. So we'll try to look at a kinetic so we can at least predict the high energy ion production, and then tune our target to minimize the high energy production, because that's really what start damaging all the mirror that I showed earlier, which is a Bragg reflected mirror. And also look at a magnetic field effect. Can we modify heat transport in EUV plasma? That's something we explore. And explore as a new concept with colliding plasma, because at the heart of the EUV is a point source, so it can be collected through a mirror. But as long as we can localize that collision of plasma into a point source, like with 13.5, that should be as valid. So, but there's physics that need to be added in PSC, which is laser ray tracing, energy deposition, temporal laser profile, and a long-term, obviously, solid density element for early time. We need to understand the early time of the laser tin interaction that we'd like to build. And obviously that could be, Will has worked, he's been doing work with Sandia with hydra simulation. And that's something we can try to tap, hopefully, as we move along with our project. So this is all I have, and to give you a possibility in the lab, but really I just wanted to just informally give you what we are doing, at least in the plasma science technology and a fusion size, going all the way to the microelectronic. And I would say that, yeah, it's exciting time at the lab, and we are really excited to have a student work with people and cross fertilize to improve this. Thank you for your time.
Thank you so much, Ahmed. That was a really wonderful talk. And it's great to see how broad the scope of activities are at the moment. First question is, what is the future of diagnostics in NSTX, ether, or fusion in general? Is laser diagnostics going to be a primary tool at some point?
Okay, I can answer this in two ways. In a fusion device, this is a very tricky thing to do because there'll be neutron. I don't know. I really think it'd be difficult. But in all the fusion facility that we have here, for understanding the physics for scalability, yes, laser diagnostic is hot in a sense that we really think that we can do more. Okay, we can add more now. The accessibility port are limited at the moment because I think it requires driving. For example, if we can show that a neutral works, I think we'll have to go and pitch it to the funding agency to have funding to install. But I would say that anything that can advance the fusion science a step further would be welcome. And laser is really something that has not been exploited to its full capability at the moment. Now, for reactors, yes, I wouldn't say hopeless. It is challenging in the sense that you really have to think about damage of windows by neutron and so forth, how to account for this.
Thank you. Ahmed, could you please stop sharing so that we can see your full screen?
Sorry.
Wonderful, thank you. There is a question from Yiguan.
Sure.
Yeah, so I mean, this was really challenging and also inspiring talk, and thank you. My question is that when you say that the power is proportional to the square of the pressure, my understanding that this might be because it's two-body reactions, which is that is proportional to the square of the pressure. But what is the role of, if that is true, what is the role of electrons and ions in the plasma? They are strongly dependent on pressure too.
Right, they all have the profile, yes. So you mean, so I'm trying to get, the ion are really crucial for getting fusion, okay? All right, so, and then you have quasi, so basically you need quasi neutrality. So you both need the electron and an ion in this case.
Yeah. In the plasma process, for example, normally that when you increase the pressure, and the termination, recombination increase faster. So therefore your ion concentration, electron concentration decrease with the increase of pressure. But your process that it seems to be proportional to the square of the pressure, that means somehow that they have different dependence on pressure, this kind of ion particles.
Right, because you have a transfer phenomena. It is slightly different in what you study in a sense because we have fully ionized plasma here in this case, right?
Yes.
So we don't have, the recombination is almost minimal at this point unless you go to this edge, okay?
Okay.
So you really, and then you have other transport effect that basically act on ion or electron differently. And so you would have, each element would have the density, pressure of the electron and pressure of ion, and then you need to be studied separately and see how they also get, you get relatively the same pressure because of collision, but as you go in a core, they become more or less collisionless. So yes.
All right. Okay. Thank you.
Thank you. And I want to remind everyone to please share your questions in the chat box. Ahmed, another question is, what does it really mean to be a group leader at PPPL? And also, what support does PPPL provide you to help you succeed?
Okay, I think a group leader, the structure of PPPL is slightly different compared to other places. A group leader is basically you building this group effectively, so you lead a group, but you have to bring the funding and then hire postdoc and research scientists time to be able to grow and have a mission for that. But I would say PPPL does provide you enough tools because you have a large breadth of expertise and you can tap the expertise from different researchers to be able to develop, to grow this group. And that's what I'm trying to do with the advanced diagnostic division at the moment. To grow that division is the way you start, you don't have anybody under you in a sense. You just have to build a team, you know. So you start with a postdoc and you add a research scientist. But there are like a way through the LDRD to increase that group. LDRD is a percentage of the funding that goes to the lab that funds the LDRD. It has to be competitive. And then also there's also solicitation through the fusion energy science that allows you to grow this group. So to answer your question, yes, PPL provide enough support through LDRD and encouragement through research because it's smaller enough community to be able to grow your program.
Thank you. And how do you usually find great people? Do you recruit people externally at the meetings, or is there any other way?
So that's a very tricky question because we've had difficulty. We have a process because we're a national lab, so we try to recruit, but usually the way it works is you basically have to get the funding first to be able to go full on recruitment. So there's always a little bit of lag here. And then you have the whole process. But we have at time, people have been recruited. That's usually at a management level. They can be recruited. But I usually go to conferences and then post and basically I'll talk to you guys, to all the faculty that have good students coming out. But we are the phase where we would like to recruit more and we don't have enough, especially in plasma science. Now, like I showed earlier, we are broadening our horizon with microelectronics. So we are not only limited to plasma scientists at the moment. For a long time, at least in the fusion science with plasma scientists. But if you go back to the TFTR era, which is one of the first tokamak that was at PPPL, the first tokamak at PPPL. So I would say there was recruitment to all with a particle physicists, and that was something good. Then it got narrowed more or less to plasma physicists, and now we're trying to broaden back that up again to hire everyone, like chemists, and then because we would like to be able to expand plasma or apply plasma to other processes, and only having plasma scientists, really, it's kind of limiting, and we'd like to broaden that.
How do you usually advertise positions?
So we usually advertise position through colleagues, through the Plasma Science Plasma Institute abroad or in the US, through the universities. That's usually how we do it. And then there's APS, obviously, and also LinkedIn and all this. So there's a lot bigger effort now through the HR department to kind of find places to advertise it. But I think it's slowly getting there, and we are trying to get on the same page as all the organizations, for example, for recruiting people.
Nice, thank you. It was amazing to hear about your truly unique experience in 4 continents. I don't think I've ever met anyone like you. It's really, really unique. So could you please tell a bit, what is your feeling? How do you fit within the system in light of your personal working style, in light of your habits, and how is it at PPPL? How do you think you fit, and also how it was in all your previous?
Okay, that's an excellent question, actually. Yeah, I'll give you my little perspective experiment on this. Is I showed you the first experiment where it was 1 man show building a device, you know, and then 5 years you do a PhD. That's all you do, and then finally. First experience, really my postdoc experience, was working with a group as a postdoc. And I would say that it was difficult. It was like torturous because I had to work with people, right? And it was something I was not used to. But you quickly develop the habit of working with people. And that really was enlightening for me because I started working with a group of people from different continents at TPFL. And from there on, you know, I grew now. I went from that group to a much larger group, which is like, well, it was one group in Australia, but working with a much larger group such as D3D and a big tokamak. And, you know, there's always an adaptation period of a year, 6 months to a year, how things work, you know, what are the unwritten rules, what to do, how you talk, what you need to discuss with people. And I would say that it took some time, and finally coming to PPPL, I know one of the main criteria for PPPL when I came here, at least that's after the thought I was told by my advisor, was like, can he work with a large group, because he's been doing this working by himself, and it's just, and that was something that I had to learn. And I would say from multiple continents, you kind of learn the way people work, and you adapt. And so I would say one of the greatest thing that I learned was how to adapt very quickly, but keeping your true self. It's always it's like impedance matching, if you wish. I don't know if for the physicist or the mechanical engineer, electrical engineer, you constantly have to match impedance. So there will be friction, challenges, but it could be overcome always with a little bit openness.
Okay. Do you have any specific advice on how to adapt without losing your soul?
I think that's tied up to personality, I would say. Yeah, I think always start with the ground rules when you start in a group, if you can, as much as possible. What you want to achieve in a year or 6 months, and then see how you basically lay that out to your colleague as much as possible, as early as possible. I would say it's always tricky to do. And as soon as you start changing focus, at least bring it up to the attention of your colleague as quickly as possible. Because what I found out in my experience, I could be working on something, a change topic, because I find something interesting, and it turns out someone has been thinking about working about it for the past 3-4 years without telling me. So then there are clashes. But yeah, I would say bring it up, and openness is really key. So it's communication. And actually, I've learned that as postdoc, where we have regular lab meetings, which is where really you have a honest team that you trust. Then you put everything down on a board, on a paper, or out there, so everyone heard you. And the more you repeat it, the more people, the more it sinks into people, and then they listen to you. And then hopefully when you switch, it's never news. It's like, okay, sure, we heard about it.
Wonderful. Thank you so much.
Yeah, thank you.
Nick Fazano has a question. He will ask.
Okay.
Hi, thank you for the great talk. My question is basically about, I guess, the future of fusion research, and sort of from your experience, these projects are so huge, like NSTX and ITER. And I guess it's two questions. One is is there any way of, you mentioned a number of different approaches to fusion, so stellarator or tokamak or spherical tokamak, and is there any way that we're going to, in the near future, sort of determine which is the best route? I guess we still don't know that. And, this is important for determining which one to build for the large scale projects. But then maybe an easier question to answer is, as you are building these large scale projects, which take a long time, there's also more research being done. So how do you sort of feed back in the more modern research into the sort of, I guess, after the design phase is done? How do you kind of feedback?
Well, that's an excellent question. That's a very excellent. It's like there's a time constant, obviously. As you build a new project, you rely on the research that was done now, and you build it. It takes about many, many years. Like either some of the physics might not necessarily be outdated, but if we had this physics, we'll probably design things slightly differently. I would say, to answer that question, that I don't know how to deal with this. This is something, so you need effectively a flexible system, but as soon as you add a lot of flexibility in a system, it becomes cost prohibitive, definitely. So hence you really have small systems, small fusion reactor that basically continue the research to improve at a smaller scale, with a mind of building a much larger scale down the road. Now, how do we feed research from other concepts? I think we look, there's some overlap. You take STs, they are really tokamak. There's some overlap. So we do listen, we go to talks, we listen to what came out, the new research. So we try to incorporate as much as possible, as long as the parameter regime is relevant. And now the question about, the other question was, how, yeah, that's a tough one. For example, how to decide which system. ITER is going full throttle at the moment, so we'll see in 2030-ish if we can get Q equal 10. But I think it's always good to have a large portfolio, and this is what is being currently done. There's private companies that are trying to achieve fusion. They're not there because they don't have the benefit of the lot of research that was done for tokamak. But I would say that your training should allow you to go from one machine to the next machine with adapting. I think that's really one of the assets of a physicist or a PhD in MAE, I would say, is adaptation. The fundamentals are fairly similar. You really have to adapt on the geometry and some of the parameter regime that are accessible. And I would say, yes, to find out the which to go with, it's gonna take some time. That's a tough question. I think we'll see the one that gives you the more fusion power. We might jump on that boat, but we quickly will find out building it is expensive. So there will be another group of research group that will try to make it small, compact, and reduce the cost, just like all engineering projects, reduce and make it something compact and small and easy to build. So I would say, yeah, it's a tough question because I don't know what's route we're gonna take.
Yeah, thank you. I think that's a great point that they're kind of related so that we can be adaptable, so that if we pick one, but then it ends up more people jump on a different boat, we should be able to also jump on that boat pretty readily.
Correct. Yep.
Great. Thank you.
Thank you.
Thank you so much. We have another question. How do you feel about the scarcity of Black people at PPPL?
Yeah, that's an excellent question. Yeah, there's not enough of us Black people at PPPL. Yeah, I don't know. This is a question in the sense that it is tough to not see enough people, and I try to really go out there in some sort of outreach so that I could convince young African-American Black people to dive in this field. Well, it did not, I would say, to be honest with you, yeah, it's difficult. I gotta put like here, I gotta change a little bit. I came from a continent where we are all Black, which is Africa. So I grew up where it was not clear cut to me. We all did our thing. Coming here, not seeing a lot bothered me a little bit, but not too much. I felt like, why? The question was mostly, why are we doing more of that? I think it's exciting, but obviously I'm biased. I think we should develop, we should have more Black people in the field. It will increase diversity of thinking, diversity of approaching problems, for sure. And one thing we just did at PPPL was create what's called the Bob Ellis Fellowship, for which we hire a fellow called Marianne, who just is going to start working with me, hopefully September, on EUV. So I think the lab is taking steps forward, but we need more outreach. We need to encourage more Black people to get into the field of physics in general, and plasma physics, I would say, in particular.
Great. And how was the situation in Switzerland and in Australia with respect?
So, with respect to Black people, I would say.
Right.
Yeah, it was also, I basically grew up, I went to college, to a French college, I wasn't rare Black people. So it was, I grew up with that basically. In Switzerland, yeah, that's, from the research point of view, it was really mixed. I did not feel that at all. Everyone was open-minded to a certain extent. It was really nice. In Australia, even more open-minded. I can think of Californian effectively, but Californian, but I would say on the other part of the spectrum, nicer Californian, I would say. No, there's no offense to the Californian, but yeah. So I didn't feel much in Australia. Or Switzerland was a little tricky, obviously, because as you know, Switzerland is a different country. It's more of a police state, very introspect, so you can quickly see differences, but that's not only for Black people, that was all the foreigners in general. So, yeah, there was a little bit of stigma for Black people being more or less how do you call that, illegal immigrant. So yeah, there was a lot of time where I needed to kind of show that, I'm not illegal, I'm here for work kind of thing. So, but yeah, from the research point of view, it was not a big deal. I was able to handle this. Yeah.
Thank you. It's really great to know your perspective.
Yeah, thank you. Yeah.
There is another question which is related to that. Do you feel the pressure to represent all Black people? I guess this is because you are the only one. And do you feel the pressure you have to represent all Black people?
No, that's yeah, no, I don't think that. That's a big load to take on the shoulder. I'll probably crumble if I try to do that. No, I think no, I definitely do not feel that pressure. I try to feel the pressure to encourage people to get in the field. So that's true. That is a pressure that I take on because I want to show the good side of doing research and the fantastic colleague that I have that really, at least, that really kind of collaborate well and work goes. And that's what I want to share the more, as much as possible, because I want to attract them to come to the field. But no, to represent all Black people, no, I don't see that, because from a paper point of view, when you publish something, they don't know if you're Black, yellow, whatnot. So to just see your paper and your work, and I think that's what should stand more so than anything.
Thank you. Another question is it usually easy to have a dialogue and collaborate at PPPL and with university?
Okay, so that's a very good question, and I think we need to do more of that. It was not as straightforward for a long time, okay? Now we're trying to open up because we realized that, first of all, there was a university that were, I wouldn't say complaining, they wanted to be more in the leadership structure of NSTX, so they can decide on the research plan. It's going to become I mean, we're trying to make it easier now to collaborate with them. So with Princeton, for example, make it easier to collaborate so we can have access to students also. It's a work in progress. It's not completely slam dunk as from university to university, because there's more protocol because we're a national lab. And that to me is it does discourage universities, because it takes much longer to get a process going at the lab than it takes at the university. So reducing the burden would be helpful, but that would have, for example, I was part of a panel, which is the Lab of the Future. What do we mean by the Lab of the Future, which is held by the DOE? And that's one of the key point that came back was, I say, we have to reduce all this burden, this hurdle that people see to collaborate with the national lab. How to make it? If we can do that, then we can attract a lot of the scientists from university and collaborate with them, which is what we really want to do. And so that is coming, and because it's coming down the pipeline, some year down the road here in a few years, we'll be able to collaborate much easily with university. But it won't be as easy as university to university. So you would have to build some a thick skin, to come work with the lab. When I say work with the lab, collaborate with the lab, because of all the protocol that is required. But I think we will continue to make an effort. And for example, I started working with Arthur and Misha Schneider. I feel like it's getting easier now. I see how it works, and I'll try to, at least from my side, how to reduce the burden for them.
Thank you.
Yep.
Another question is, how did the current pandemic affect your collaboration with ITER and also the construction of ITER?
The construction of ITER, I think it did affect, but I'm not sure the detail. The thing in France, in the south of France, they started working a little bit. They got out of the pandemic a little quickly than we are doing right now. So to answer your question, yes, it did affect. I have a collaboration with an experiment in West, which is in south of France also. It did affect that. It slowed down our project, where things we were supposed to build and ship over there got slowed down because we couldn't be in a machine shop, for instance. So yes, it does affect by a few months, 2-3 months, if not more now. Now it's expanding. It's a bit unfortunate. For example, starting a lab for EUV has been delayed also. So in many ways, I would say it did affect. But in a grand scheme of stuff, because it affected everyone the same way, so the relative to other project, maybe the theory project got more advanced, but I would say that it's okay. You know, we're all in the same boat, so we are kind of plowing through this pandemic slowly. But yeah, to answer your question, yes, it did affect, and but it just delayed the research output by a year at least.
Thank you. Another question is, what is your favorite part of working at PPPL?
That's I think it's a freedom. I think PPPL is one of the national lab that I would say that has a little bit of academic freedom that I really enjoyed when I came to PPPL because I was a free thinker. I wanted to do stuff outside the box. Yeah, you were less boxed into a topic. You're allowed to kind of come pick your topic of interest. You have to also have a percentage of your work that kind of align with the main goal of the lab, obviously. But I think the free thinking helps a lot here. The academic aspect of it, not completely like a faculty, but to a certain extent that we had more of that I would say most national lab have. And that's because we are affiliated with Princeton. I mean, we are with Princeton University, I would say. And that I enjoy. And I think the collegiate approach of research with my colleague is really something that I do appreciate. We can talk to each other. The doors are more or less open all the time, at least with this group, It took time to get to this level, but I would say that at this level, yeah, that's what I enjoy the most. Yep.
Great, nice. And is there anything you find difficult over the course of your career? Maybe now not, but.
Right. I think the thing that I found a little bit tricky at the lab was effectively that we are both let me put like in simple term, we are both like seen as research scientists, but also as research scientists slash faculty. So for example, our promotion really is seen almost as a faculty to a certain level because it is done by Princeton University. But at the same time, we have a mission. So we're mission oriented. And so it gives you less freedom. You really have to tie yourself in a lot to the mission to be able to advance in your career if you want to, if that's what one of your goals are. So I would say that I find difficult, and I hope that changes down the road, because I think we're very mission driven, and we should also we should not be pegged too much to a faculty scheme where, you have to bring grants. I mean, and it's good to bring grant, but I think that's when you want to do something different. But, publish a lot, because sometimes it's a group effort that kind of allows you to drive the mission as opposed to individualistic. So this is something that we are right in between and a cusp of the book. So I feel like sometimes I find it difficult to navigate that, especially as a young postdoc. When you arrive, you're like, how do I navigate this? But as you get older, you realize, okay, more senior, you realize, okay, I could deal with this. I know I could I could change. I could have like priorities as a year goes, and then see where I am. So, yeah. So to answer your question, yeah, that's the difficult part, I would say.
Thank you. And speaking about the mission,
Yeah.
That may be difficult, but what is your personal mission in your research, in your work?
So I like I said, one of my first I like to understand some fundamental physics, and fundamental aspect of I like to go down to the nitty-gritty detail, fundamental of a system, like apply the edge of the plasma. So that's what drives me the most, and that's my mission. And also, I really, really get excited about novel approach to getting information on the plasma. So remote sensing, for instance, what's the best way to probe a plasma and get information that you can never you did not get or you could not get, and as direct as possible. So so I've been really, as you can see, my career, but I'd be interested to get a direct information. And I know it's always challenging. And I feel like because we're mission driven, that tends to be put aside. Once we have globally a sense of how to get the information, we leave it. But I feel like we should be continuing to innovate. And that's what really drives me, innovation, and that's excites me. So yeah, that's one of my goals, continue to innovate.
Thank you so much.
Yeah.
It's a great message to wrap up.
Right, thank you. Thank you very much for inviting me. I really appreciate this and great questions. And you have my email on the slides. So if any student wants to ping me for other question, my experience, I'll be glad to offer those.
Thank you. Thank you for sharing your unique path with us and all the advice. I really find them very useful and insightful. Thank you so much. And thank you everyone for participating, and have a great day.
Yeah, you too. Thanks, Julia. Bye.
Bye.